How's it going, everyone? How's everyone doing today? Were there any questions about section 6.1? Or, yes, that's where we're at. Sorry. We'll get to part 2 of the project after we take the test on chapter 5 and 6. So our test is Tuesday next week. And I'll make sure I upload the review today so y'all can start looking at it, and we'll go over the review in class on Thursday. So next Thursday, we'll talk about part 2 of the project, and I'll go ahead and give you all the work for that then. Okay. Part 2 won't be quite as involved as part 1, so it should be a little bit easier as a result. Yeah. Okay. So today we're going to look at section 9.2, which is on the binomial probability distribution. Okay. Now, a probability experiment is called binomial if we can define outcomes as, well, we can define outcomes in we need two outcomes, is what it amounts to. Binomial, bi means two. So if we can define the experiment as having two outcomes, which we designate as success and failure, then that would make it a binomial experiment, or probability experiment. So a probability experiment is called binomial if its outcomes can be classified as either success or failure. Okay. So, essentially we're saying that the experiment has two outcomes. I mean, there may be more than that, but we're able to boil it down to two outcomes, whether we're successful or it's a failure. Okay. So we say that let P be the probability of success. Well, yeah, P be the probability of success. Q, and again Q is equal to 1 minus P, is the probability of failure. Notice that if we have success and failure, because there's only two outcomes, they're naturally complements to each other. That means the probability of the two events has to add up to 1. Therefore, we'll be given at least the value for P. We may not be given the value for Q, but we can always find Q by taking 1 minus the value of P, because they are complementary probabilities. Okay. Because the complement of success is failure, and vice versa. Okay, so we have P and Q. N is the number of trials. Now, when we say trials, this is the number of times the probability experiment is repeated. Okay, and finally, X is the number of successes in those N trials. Okay. So that sets up our notation. We have P, probability of success, Q, probability of failure, N, number of trials, and X, the number of successes in those N trials. And so what binomial probability will help us find is the probability of X successes in N trials. That's ultimately what we're going to be looking at with our formula. Now, the formula is somewhat unwieldy, but we will be able to use technology to work around it. So that's kind of nice. Let me show you what the formula is first. Oh, sorry about that, Becca. Yeah, if I'm writing and my hand's moving back and forth, doesn't always show up clean. There's the image again if you need to see it with some clarity. Hopefully that helps. And again, if you need to, you can pause it right here when you're looking at the video again and look a little more closely at this now that you can see it clearly. Sorry about that. Anyway, normally it's pretty good, but every once in a while it gets stuck out of focus. So P of X is equal to N factorial, which we use as an exclamation mark, over X factorial times N minus X factorial times P to the X times Q to the N minus X. Okay. Now, This first term, we haven't really done anything as far as I remember with the factorial operator. So if we have 3 with an exclamation point, doesn't mean that we're really excited about this 3. 3 factorial means that we have 1 times 2 times 3. Okay, we multiply all the numbers from 1 up until we get to this number listed here. So if we had 7 factorial, we 1 times 2 times 3 times 4 times 5 times 6 times 7, and we just multiply all of those together, and that's 5040, of course. That's a 6. All right. So that's what the factorial operator does. And so we have this expression here, n factorial over x factorial times n minus x factorial. This is part of section 5.5, which we did skip, but it's on counting. And basically this number represents the number of different ways that we can have x successes in n trials. Okay? We think about it like this. Let's say we have a basketball player that shoots 20 free throws, and we want to, maybe they have a lifetime free throw percentage of 75%. They make 75% of their free throw attempts. Okay, what is the probability that this particular basketball player makes 14 out of those 20 free throws? That would be 14 successes in 20 trials. Now, the problem with that is we know that we want to calculate how likely it is that they would have 14 successes in 20 trials, which should be pretty good. Not like 50% good, but pretty high. But what the problem is, we don't necessarily know the order that they would come in. It could be that the person makes 14 in a row and then misses the next 6. They could make the first 5 and then miss 7, and miss 6, and then they make the last 8. I don't know if that has 20. Sorry. And it could be in any order. They could miss the 2nd, the 5th, the 9th, the 13th and 14th, and then the 17th. We don't know exactly which ones are their misses in order for them to have 14 out of 20. But the idea is that we don't have to know. We can count a number of different ways it's possible to make 14 out of 20 using this calculation. And that's what that number represents. And we don't really need to go into it any further than that. But basically, it's a counting of how many different ways this could happen. And then we have the rate of the probability of success raised to the power of the number of successes, and the probability of failure raised to the power of the number of failures. Because if we have x successes in n trials, then we have n minus x failures. So anyway, this is a pretty crazy formula. And what really makes it difficult, well, I'll talk to you in a minute about that. Let me go ahead and show you how we would do that problem I just described with the basketball player and the free throws attempts. Now, let me write down the problem first. Let's see, historically, a basketball player has hit 75% of their free throws, or free throw attempts, if they take 20 free throws, what is the probability that they are successful in 14 of those? Okay. Now, the reason this is a useful example for binomial probability is that this is very clearly defined what success and failure is in this case. Either they make the shot and the ball goes into the basket, or they miss it, however that happens. And so we know that they have a success rate of 75%. That's our p-value. So we can say p is, and we should make that a decimal, 0.75. Which they're taking 20 free throws, so that means the number of trials is 20. And we want to know how likely it is for them to be successful for 14 of those 20 free throws. So we're saying x is equal to 14. Okay. If p is 0.75, the probability of success, what is the probability of failure? What would q be? Anyone have an idea for that? If 75% is our success rate, then what is our failure rate? Okay, well, 75% of chance of success will be 25% chance of failure, so Q will be 0.25. Now, fortunately, we don't actually need to know what Q is, I believe, when we put this into the calculator. What we'll use in the calculator is actually strictly based on P, N, and X. Since Q is based on P, we don't actually have to know what Q is. In fact, we could rewrite this original problem, or the original formula for P of X. Instead of putting Q here, we can just put 1 minus P raised to the n minus X, because we know that that's the relationship that those two values have. Okay. So that's what we have in this question. We have a 0.75% chance of success, 20 trials, and 14 successes. Now, on the calculator, we want to use what's called the Binomial Pdf Distribution. PDF means probability density function, but basically this will be our binomial probability we can use it for. On the 83s, and I think the 84s are similar, we would press stat, go over to tests, not tests, calculations. Wow. I missed it somewhere. I'm going to check my notes real quick. Oh, here's distribution right above the vars button. Sorry. Let me make sure y'all can see that. Yeah, right here. This is our distribution, so that means that refers to our statistical distributions, probability distributions. So that we have to hit second and vars. Sorry about that. And here we go. And we'll need some of these other ones eventually. But if we go down to, well, on the 83s, it's 0 and then A. And I think on the 84s, it's like A and B or 9 and 10, one or the other. And it's a little bit off on the, if you have a TI-84 instead of the 83. But we have both of those there. And so we would press enter. Now on the 84s, or sorry, the 83s here, it doesn't really prompt us for these three values, but the order that we need to use is N, P, and X. So for the TI-83, we use Binomial Pdf N, P, and X. That means we'll enter the value for N first, put a comma, and then the value for P, and then another comma, and then the value for X, and then close parentheses. So N is 20, P is 0.75, and X is 14. So we'll put 20, comma, 0.75, comma, 14. And PX, okay. I did it correctly. Oh, that's not a comma. Comma. There we go. Alright. So, that means we have almost a 17% chance, it's 0.169 if we round, probability, so almost 17% chance that this basketball player will make 14 out of the 20 free throw attempts. Okay. Need a bookmark. Goodness. I threw all my paper in that pile. Oh well. Probably alright. If we look in the appendix of the textbook, okay. Our appendix, we have a bunch of tables. I may have mentioned a random number table previously where we had to blindly spin our pencil around and land on some point or the other on this table. And pick however many numbers we need. So, anyway, if we go after that, we get to table 3, which is now sideways, of course. Table 3, this is our binomial probability distribution. And it has n and x in the first 2 columns here, and then p going across the top. So, if we need 20, okay, here's n equals 20. We need x is 14, so we come down to the row 14 here, which, there we go. And then we go across on the top to where p is 0.75. And what I'm going to do is I'm just going to move my finger down and across. I think I found it. Okay. And it actually gives us that same value. This is 0.1686, and that's the same number that we got in the calculator already. Okay. So we are able to get the same result from this table. Notice the table, though, only works for specific numbers. It actually stops at n equals 20, so it doesn't go higher than 20. And if you look at the percentages, they're largely just increments of 5%. It doesn't hit like any values in between. Now, what I will do, as far as what I assign for you on the review and on the test, is I'll make sure that what I assign, you can either use your calculator or you can use the table to look up if you prefer. Calculator will be easier overall, but the table is still an option. Okay. So we are able to get the same results. Now the table is just all these calculations that would have to take place already pre-calculated for us. We just have to look up the one that references what we need. Okay, so it works for n up to 20 with, again, counting from 1% to 5% and then counting by 5s up until we get to 99. I'm sorry, 95, and then actually we don't even get 99. So, let's look at the other calculator, the 36x. Now the 36x is closer to what you'll see on the 84s if you have an 84. Now notice in this case, distribution is actually right above the data button. This is what we used previously. So here, previously we used the 1var stats button, but now we just arrow right to distributions. We'll go down to option, I think it's A, or no, not nearly as many this time. It's option 4. Sorry. And press enter. Now, we have the option of using a list of values, which we could do that, but it's probably easier to just do the single values. And so trials, n equals 20. Probability of success, we have 0.75. And number of successes, we said 14. We go down and we say calc. And so it gives us the same result, 0.1686, and continuing from there. I think the 84s are largely the same in the sense that rather than us having to know what order the numbers have to be put into the calculator in, it'll actually prompt us for, like, okay, this is the number of trials in, this is our probability of success, this is the number, this is X, the number of successes. So it is a little bit more helpful in that regard because it guides us as far as how we enter the numbers. So, all right. On the files section of Canvas, I went ahead and uploaded calculator instructions for binomial distributions. Now, we've only really looked at the first option for each calculator, TI-84 and 36X, and then 83s. But we have some more options that we need to look at, which is where X is not just a single value, but X is a range of values, less than or equal to, which is 0 to X, or greater than, which is from X to N. I guess it's greater than or equal to, sorry. Yeah, my writing was not entirely clear there, but that file is already in the files. I added it to the same folder with the formula sheets and the calculator instructions, so that's right there. I'll make sure I include it with the exam, like in the instructions. I'll make sure that's included kind of as a formula sheet, but you know, it's more instructions on how to do it. Okay. So, let's look at those other scenarios I mentioned. And let's stick with our basketball player that has a 75% chance of success. Okay. What is the probability? Our basketball player makes at least 17 of those 23 free throw shots. And again, we know the probability of success on a single throw is 0.75. Okay, so if we say at least 17, does that mean 17 or larger or 17 or smaller? Well, if we say at least 17, that means it could be anything from 17 through 20. Okay? Yeah, 17 or larger. if we say more than 17, that would actually be 18 to 20. If we say at most 17, that would be from 0 to 17, and if we say less than 17, that would be from 0 to 16. So depending on how we phrase this, there's 4 different ways we could really interpret what's happening here. Okay, so these are kind of the 4 different ways we might see this written, but we know in this case, this first one is what we're focusing on, which means, so the probability of making x greater than or 17 free throws would be the probability of making 17 plus the probability of making 18 plus the probability of making 19 plus the probability of making 20. Okay? So what happens is if we have a range of values like we have here, rather than just a single value, that means we have to calculate the probability of each of those values and then add them together. Now, again, the calculator is set up to do this for us in one step rather than the 4 steps, thankfully. Even if we look at the table in the back of the book, we just have to add up those 4 values, because we'll see the 4 values listed on that page. Anyway, but yeah, this is what we're looking at here. We just want to make sure we interpret what is being asked correctly. Whether it's, starting from 17, is it 17 up? Is it more than 17, 18 to 20? 17 or less, which is 0 to 17, and then less than 17, which is 0 to 16. So, really 4 different ways we could go from there. Okay. Now we wouldn't ask anything crazy here, like what is the probability that they make an even number of free throws? It doesn't really make much sense, at least in this scenario. But there's not a lot of scenarios where that would make sense. So generally, we're going to be interested in an interval of values like this, or we're going to be interested in one specific value, like we saw in the last example. Okay. So the question is, how do we do this on the calculator? Well, you may have noticed, like I showed you on the screen before, I did have instructions for these other things on the calculator. Now, I'm going to open that up again so I can see it. And we'll use the 36. So let me show you these instructions. So for the 36 calculator, if we want x less than or equal to a value, or 0 through x, then we follow these steps. And if we want x greater than or equal to a value, which is from x to n, then we'll follow these steps. Now, basically, what's happening here is if we want probability of x is greater than or equal to 17, what we actually calculate is the probability that x is less than or equal to 16, and then subtract it from 1. That's because whether we make 17 or more, or 16 or less, these are 2 complementary events. This contains all the outcomes from 0 to 16, and this contains all the outcomes from 17 to 20. And between them, they represent all the outcomes possible. We know that we can't make 16 and a half free throws, so we shouldn't worry about what's in between 16 and 17. We're only working with whole number data here. That's why it's discrete, and that's why it works here. And so we use the concept of complementary, because the way the calculator is set up, is it can only calculate these less than or equal to probabilities on the calculator. We can then subtract it from 1 to get the greater than or equal to probability. Okay? Let me turn that off. Alright, so we can set up x greater than or equal to 17 equals 1 minus the probability of x less than or equal to 16. Those are our complementary events. Now, the way that we do x less than or equal to 16 is, for that one, we use the binomial CDF function on the calculator. In this case, C means cumulative density function, which means we're actually combining all of those together. So we use binomial PDF for one value, but binomial CDF for a range of values. Okay. So we do second data, arrow right to distribution. Should be option 5 here, binomial CDF. Enter. Now, that's 20, that's 0.75. Now, the question is, what do we enter for x? Well, we enter x as 16 in this case because we want everything less than or equal to 16. Okay? So this will find the probability of everything from 0 to 16. Whatever x value we enter, it finds the probability of 0 up to that number. Okay? So press enter, calculate. And so the probability of making 16 or less is 0.775 if we round to 3 decimal places. Okay? Which, when we subtract those now, that gives us a probability of 0.225. So, almost, well, a 22.5% chance that we make at least 17 of the 20 free throws, given that we have a history of making 75% of the shots that we take. Now, let me caution you that I'm using sports statistics as kind of an example here, but realistically, the probability of success for an athlete is constantly in flux. It's constantly being recalculated based on their successes as time goes on. So we can't say for sure that's what's going to happen to a particular athlete because there is a human element involved. And so, at least with free throw shots, it's a little bit safer because they're not being impeded in their attempt to make the shot. But overall, we can't really give a concrete probability for sports statistics. We can look at what an athlete has done in recent history, whether it's the last month or the last week or the last season. We can look at that, and it should provide some element of accuracy, but it won't be completely true necessarily because we never know what's actually going to happen until it happens. And it may be that this particular athlete on this day is only going to make 50% of their free throws, and I mean, we may not be able to predict that with our probability model here, but that may be what actually happens. So realistically, sports statistics are not a great example here, but I think it's a more relatable example, so I'd like to incorporate it. Anyway, that being said, let's continue with this. Okay, so we're able to find the probability that at least 17 free throws will be made. It's 0.225. Again, if we look at the textbook, again, going into the appendix like we did before, I missed it. There we go. Okay. So again, we have n is 20. Now we want 17 through 20, these last four numbers. So we go over to the column where we have 0.75% success, which is this column right here. Whoops. And so what we would do here is we would add together, this is 17, 18, no, sorry, this is 17, 18, 19, and 20. And we would add together these last four numbers, and it should equal what we just came up with, which is 0.225. So we would add 0.1339 plus 0.0669 plus 0.0211 plus 0.0032. Yeah, and it comes out to be about 0.225 like we saw. They'll round to it at least. So that's giving us the same number just from the table instead. As I said, I'll make sure we're able to use this table on our calculations for this problem, because I know not everyone has a graphing calculator. Okay. We should. It's again mentioned as a course requirement, but I understand if you're not able to. And normally in a classroom setting, if we were actually sitting in a classroom like we would have been, I would be able to hand out some of our calculators just for y'all to borrow for the period and give you the instructions, and you should be okay. Unfortunately, we're not in that scenario right now where that's possible. So anyway, I wanted to make sure this was an alternative for others, because I don't want anyone to have to use that formula. That formula is just unwieldy and tedious. So this is better than nothing. All right. So one other question here. We looked at least 17. So another question we could ask is, what is the probability that our basketball player makes less than 7 free throws? Now, if we say less than 7, then what interval of outcomes does this indicate? Similar to how we talked about on the previous sheet. We said at least 17 was 17 through 20, more than 17, 18 through 20. Yes, 0 to 6. Yeah, so less than 7 means 0 through 6. Good. So when we put this into the calculator, we'll use Binomial CDF. N equals 20. P equals 0.75. And we'll use x as 6. Okay? Whatever the highest value here is, 0 to whatever, that's the number that we use for x. Okay? And that's why we have to be careful, because we would be very tempted in this case, the way the question is worded, to try to use 7 as our x value, but in fact it's 6. Alright. So on our calculator, second data, arrow right, down to option 5. Now, one thing we could do, just as a quick shortcut on our calculators, if we know it's option 5, we can just press the 5 button and it goes right to it. Okay. So if we're doing it multiple times, we might get the hang of that. Anyway, 20 successes, 75% chance of success, and we'll use x as 6 in this case. And go to calculate. And it's actually a very low probability of this happening. So it's about a decimal point and then 4 zeros, and then we'd say 3, I guess. Okay. 4 decimal, 4 zeros, yeah. It's 2 9, so we'll round to 3. So 3 chances out of what is that, 100,000 that this basketball player would make 6 or less, when historically they have shot 75% chance of success. Okay, that means the higher the chance of success, the lower the probability of having disastrous outcomes, such as this, where we make less than 7. Okay. Now, this is going to be approximately 0, and probably what we'll see on the textbook. Actually, let me show you, because I have my suspicions here. I already closed the book again, so I have to find it. So that's the whole thing. And I've got it already. Okay, so we have n is 20. We're making sure we're looking at this bottom table here. We want 0 to 6, which is basically the first 6 numbers here. Or actually, yes, from 0 to 6 is actually 7 numbers. But we go over to 0.75%, or sorry, 0.75, and we go down. This is where it hurts not having a bigger screen. We notice that 0, we basically have a bunch of zeros. Actually, all the way up until 7, where we finally get something besides just zeros, which is 0.0002. So basically, we see these numbers from, these are all the numbers from 0 to 6 right here. And all of them have this 0.0000 plus, which means there are numbers after that, but it's so close to 0 that it basically rounds to 0. I mean, we already have 4 decimal places of accuracy here, and it's still not registering. So what we would do here is we add together all these zeros, and we would say it's nearly 0, which is our probability, which is correct, because 0.00003 is very small probability of occurring. Okay. But what we would do is we'd add all those numbers together from 0 through 6, right here. And we would just write down 0 as our answer in that case. The plus means it's approximately 0, because it actually goes on. The decimal does go on beyond that, but it's such a small number that in order to save space in the textbook, they just didn't even write this down. Okay, so if we do it on our calculator, we'll get a little bit more accurate result, but even then, you know, the book is basically going to say, well, we've only been rounding to 4 decimal places. That's what we get. So, okay. So if it comes out that our probability is that low, I'll be pretty forgiving as far as the calculation there. Alright. The last thing that we want to cover in this section is the mean and the standard deviation. As we always do, it seems like, but it turns out that these calculations are much easier than from previous probability distributions. So our mean, mu, is equal to n times p, and our standard deviation which is sigma, is equal to the square root of n times p times q. Or, instead of q, we could say 1 minus p, either way. Now, for our basketball player, where we know that n is equal to 20. We're taking 20 shots, and we have a historical success rate of 0.75. So for the mean, we just multiply those two together. 20 times 0.75. So on average, the basketball player would expect to make 15 out of 20. And if we look at our table, that's actually the outcome that has the highest probability of any number from 0 to 20. Then our standard deviation, sigma, would be square root of 20 times 0.75 times 0.25. If 0.75 is our probability of success, then 0.25 is our probability of failure. So we would do 20 times 0.75 times 0.25, and I forgot to take the square root. Let's see, so square root of our answer. So 1.936 would be our sigma. So, standard deviation of about 2. We're going to explore the interaction between mu and sigma a lot more closely in Chapter 7. So that'll be coming up still when we look at normal distributions. And that will be a lot more calculator work. So if you don't have a calculator, I still recommend that you get one, especially for that last couple of chapters, 7 through 10. It's really vital, I think, as far as helping our success and working around a lot of these complicated formulas, I guess I say. Anyway, I mean, these are not complicated, but the binomial distributions, we definitely would like to have a calculator doing that work for us rather than having to look it up on a table. And the same is true for the Chapter 7 material. Alright. So that's all I have for you today. I don't have any homework for you because instead I would like for you to look at the review and go ahead and practice on that. But on Thursday's class I will go over the review as well during that class period. So I would suggest looking at it in advance. That way you kind of have an idea of how you're doing and maybe what things you need to focus on. But yeah, the review will, again, very generally show you all the types of problems you should expect to see on the test. Okay? At some point, I will actually grade your projects. I'm not quite sure when I'm going to get to that, though, unfortunately. Maybe next week while you're doing your tests. Anyway, but I'll try to get that done next week and have those projects graded before I sign the next one. So, anyway, I think we'll go ahead and stop there. So you all have a good rest of your day, and we'll continue on Thursday with everything. So y'all take care, and I'll see you then. Bye.